Okay, good morning, guys. So today we will continue week 10 lecture. And last week we stopped at the in-plane flexion and shear strength for unreinforced masonry walls. So this is actually the shape of the typical shape of wall. So we have vertical forces. Sorry. So we have some vertical forces, B, and horizontal forces from wind or earthquakes, F. And these two types of forces will cause like moment in this direction from the horizontal forces. Okay, this moment will cause some problem at this end, which is crushing, may cause crushing, one of the problem at toe. Another problem is this wall may overturn due to the moment here around this point. And also one other issue can happen is tension in this side, so might have some like cracks here or here, tensile cracks. And this force also can cause like, sorry, sliding shear here. So this force will cause sliding shear. So this is the force issue. So these are force things we need to check when we design the unreinforced masonry wall for in-plane flexion or shear strength. So let's continue at last step we reached last week. So this was like a summary of what is the issues or what is the checks needed. And today we will go through them in detail. So our first issue, or our first check is crushing at the toe. So when you have the force, the horizontal force here, F. So this force is again from wind load or earthquake load. And this is our B from vertical loads or gravitational load, dead load, and life load. Okay, so first of all, the load combination we have in this case to check the wall for crushing. For vertical loads, B, we have the combination 1.2 dead load or G plus psi C Q. So our load combination 1.2 G plus psi C Q. For the horizontal force combination, F is directly the wind load because the wind load already ultimate load, so it's already factored. So this is our check. Again, the problem is we may have crushing due to compression here on this side of the wall due to the moment or the applied moment from horizontal force. Okay, so the formula we will be using is B, the vertical load or the vertical force over AB. AB is the bedding area of the masonry element plus F is the horizontal load times H. What is H? H is the lever arm or the height of the wall. The actual height of the wall is H. So FH is actually our moment. So FH is the moment due to horizontal force. F times H. F times H is the moment divided by ZD or the section modulus of the bedding joint. Okay, so the stress due to these two, the vertical and horizontal load, should be less than or equal to phi Fm dash. Okay, y phi is the reduction factor, while phi is the reduction factor, and fm dash is the probability of the masonry, unreinforced masonry, and z is the section modulus equal to 2 times ts b squared over 6, where b is the width of the element or the masonry wall element, and ts is the thickness. Okay, so what we need to know here, the load combination, this one, not work. So we have the load combination and the formula. So the load combination, 1.2 dead load plus psi c life load for vertical forces, and for horizontal forces we have the wind load or earthquake load, and the formula we have B over AB plus F times H over ZT, the section modulus, should be less than or equal phi Fm dash. Okay. And then our next issue or our next check for unreinforced masonry wall is tension at the heel. So tension at the heel also due to the moment on the wall. So we have this is F and this is H and this is B. So the moment will be something like that. So it will cause some tension on this side of the wall. So also we can have cracks. So this is tension at the heel. So for unreinforced masonry, because it is weak in tension, so we need to be careful when we design this type of wall and check if we have any possibility of tension. The load combination for this case will be for vertical load, only consider the destabilizing load, which is B equal to 0.9 G. For horizontal load, F, we have F again equal to W ultimate or E directly, or earthquake or wind load directly. The formula we will be using is almost same formula, B over AB. So B is the vertical load, AB is the bedding area of the masonry element, F is the horizontal load, H is the wall height, and ZD is the section modulus of the bedding joint. And here FM FMS is the design characteristic shear strength, FMS, according to clause 3.3.4a, and can or shall be taken as 1.5 of FMT dash, not greater than 0.35 MBA and not less than 0.15, sorry, 0.15, sorry, MBA. So actually FMS dash equal to 1.25 FMT dash and should be between 0.15 MBA and less than 0.35 MBA. So this is the main formula for, or the main value of FMS, but you need to be between the range 0.15 and 0.35. Okay. Do you have any question, guys? Harrison and Brendan? No? Okay, so this is the strength we are comparing to, And if we here again, just do a definition for Fm dash here. For Fm dash, it is a compressive strength of unenforced masonry in general. Of masonry. Okay. So this is Fm dash, and here is FMS dash. The third issue we need to check for unenforced masonry walls under in-plane loading. So we have the overturning at the toe here at this point. So due to the force, the horizontal force and the lever arm edge, so we will have a moment applied here, M equal to F H. This moment may cause our unenforced masonry wall to like overturn like that. Okay, so this is our F. So we need to check that our wall is stable against this overturning. So the load combination in this case, we have for vertical forces B equal to 0.9 dead load or 0.9 G. For the horizontal force F, again, it is F equal to WU or the wind load. So this is similar to the tension at heel. So in this case, the overturning moment is F times H. So this is our overturning moment. And actually what makes the wall stable or what try to stabilize the wall? What to try to stabilize the wall is the moment due to the vertical forces B. So we have, this is our resisting moment generated or produced by the vertical load. Okay, this moment will be if this our wall width. So this force acting at a distance of B over 2 from this point. So our resisting moment will be the vertical force B times half of the wall width, which is B over 2. Okay, so the resisting moment is B over 2, and the overturning moment is FH. So our formula for stability or our check formula is the stabilizing moment or the resisting moment B times B over 2 should be more than or equal to a factor of safety times the overturning moment FH. So we have, this is our resisting moment, and this is our overturning moment. Okay, so our check means that we need to confirm that the resisting moment is more than the overturning moment. Our fourth check for these walls is shear capacity of the wall enclosed 7.5.4 in AS 300, sorry, 3700 2018 version. So we have two type of shear stress. We have sliding shear failure or sliding failure. Okay, this when we have something like shear stresses at this point. So the wall slide at this red surface, sliding surface. Okay. Another type of shear failure is the diagonal shear failure. So diagonal shear failure is something like that. We have this crack. Okay, this crack can be within the, as you know, we have some bricks. So this can be within the bricks. Okay, so we have shear crack, diagonal shear crack like that. So these are two types of shear failure due to the in-plane lateral force or in-plane lateral loads. Okay, to check the horizontal shear forces, we have two type of shear forces, the horizontal shear force and the vertical shear force. So for horizontal shear forces, our formula is in clause 7.5.4.1. The formula is V design should be less than or equal to two components, V naught plus V1. So the shear capacity of the wall comes from two components. The first component is V naught, which is the shear bond strength of the section. The second component is V1, which is the shear friction strength of the section. So the shear capacity comes from shear bond strength, the bond between the wall, the masonry, and the mortar, and so on. And the other is the friction or shear friction. Okay, so V naught equal to phi FMS dash AD. So this is our V naught value. And V1 value is KV times FD times AD. So phi is the phi is the capacity reduction factor from clause 4.4. FMS dash is the characteristic shear strength from clause 3.3.4. AD is the design cross-sectional area of the shear resisting portion of the member C clause 4.5.6. Okay, so depend on the clauses 4.4 and 3.3.4 and 4.5.6, we can find how much is V naught or the shear bond strength. The other is the shear friction, which equal to KV FD AD. KV is the shear factor given in table 3.3. FD is the minimum design compressive stress on the bed joint at the cross section in a member from clause 7.5.5, but not greater than 2 MPa. So FD has a limit, should be less than or equal to 2 MPa. Okay, so after you find these two components, FD should be less than this two component added together. So this for the horizontal shear force. For the vertical shear force, so V design in the vertical shear force should be less than or equal to phi FMS dash times AD. So as you can see, FD here is similar to V naught here. So if VD here should be compared to same formula of V naught here. So we can mention that this value is V naught, or it is the shear bond strength of the member. Okay, so this is VD, where VD, the parameter to calculate VD are phi, the capacity reduction factor from clause 4.4, and FMS dash is the characteristic shear strength from clause 3.3.4. AD is the design cross-sectional area from clause 4.5.6. So it's a similar formula for the part of the horizontal shear force. Okay, and that's it for the unreinforced masonry. Do you have any question, guys? Okay, thank you. So now let's move to the second part we have today, or second topic we have today, which is reinforced masonry. So reinforced masonry is masonry elements reinforced with steel reinforcement. So let's start to revise the masonry in building. So review on masonry in building. Masonry walls are commonly subjected to out-of-plane lateral loads. Most commonly, these loads are either wind or earthquake loads. So as you know, if this our wall, so the wall are subjected to out-of-plane lateral load or lateral force from wind or earthquakes. The design is normally based on the load combination point 9 G plus WU for wind load. So our load combination is, or the main load combination is point 0.9 G plus WU, this for out of plane and in plane. The response is dependent upon the boundary condition of the member, vertical moment or vertical bending, horizontal bending, or two-way bending. So we have three types of bending if you refer back to the last week lecture. So depending on the boundary condition of the wall, so if this our wall, we might have boundary condition to the vertical side, and also we might have boundary condition for the horizontal or the top and bottom uh, edges. So we have top edge, bottom edge, and vertical side and vertical side. So depending on the boundary conditions of these four edges, the behavior of the wall will be decided. So for example, we might have our first bending is a vertical bending for this type of wall. So as you can see, we have top edge is restrained using this red boundary condition, and also the bottom edge is restrained. So bottom edge restrained as well. So this means that the sides are free and free here. So what happened to the wall? This wall bent in the vertical direction like that. So it is like this is our original wall. So this one will be or will bend like that because we have horizontal support at the top, support at the bottom. So if we look at this one here, so we have support at the top here, support at the bottom line here. So the wall bent in this direction like that, causing what? Causing cracks in this direction or in this joint here in the middle, because this is the point of the maximum bending. Okay, and the failure here happen on the bed joint. So this is called vertical bending of the masonry walls. The second is horizontal bending. Second bending behavior is the horizontal bending, which is quite similar but in the other direction. So if we have a wall, like this wall, in this case, the wall is restrained at only the two vertical sides. So we have vertical restraint here and vertical side restraint here, and no restraint at the top or the bottom. So here the wall in this case will bend in the horizontal direction because we have a support here and support here. So our bending will be in this direction. So the cracks will happen like that. So if we look here, so we have a line of support here, vertical restraint. We have another line of support here, vertical restraint. So this is our system, and our bending will be something like that. So the maximum moment here, so as you can see, the cracks happen like that. Okay, so this is our crack or failure at the pre-bent joints, which is the vertical joints of the wall. The third, or this is just a reminder of the one-way horizontal bending. The horizontal one-way horizontal bending The horizontal bending may fail either through the mortar joints or partly through the joints or partly through the masonry units. So as you can see here, this failure line can happen in the masonry unit itself or part in the masonry unit and part in the joint. So in the unit or in the unit and joint. Okay. All prevents must be completely filled. The wall must comprise a minimum of 4 continuous cores of masonry acting together in horizontal bending. So each line is one core, so 1, 2, 3, 4. So this is the requirement. So the wall must comprise a minimum of 4 continuous cores of masonry acting together in horizontal bending. The design formula is MDH should be less than or equal to MCH. So H is for horizontal bending, and here also H is horizontal bending. MD is the design moment, so design horizontal bending moment. This is the design moment, and MC is the moment capacity. So similar to any design formula, the design moment should be less than or equal to the capacity for Thank you, Hassan, for the question. The column is a vertical restraint only if there is a connection between the column and the wall. So they need to embed some like connection between the column and the wall. But if it is just attached to it without any like embedded connection, so it is not considered as a vertical restraint because it will be too weak. Okay. So this just was a revision of what we have done last week for the one-way horizontal bending and one-way vertical bending. And the third type of bending behavior is the design for two-way bending. So the actual crack pattern is similar to slabs or concrete slab. So the actual crack pattern depends on the support or restraint condition on each side of the wall panel. So we have again four sides: top, bottom, and vertical side left and vertical side right. So for the two-way bending, you might at least have one restraint at the bottom and one restraint at vertical, one of the vertical side. So one horizontal strain and one vertical strain. Okay, so as you can see here, this is an example of for the two-way building. So in this case, we have this side of the wall is supported by another wall. So we have a line here. We have also a support at the bottom side of the wall here. And we have a line of support at the top of the wall here. So only the right vertical side doesn't have restraint. So as you can see, we might have a crack line here or fold here at 45 degree, for example. And also here, because we have like two supports, two line of support here. Then this will intersect at this point. Then the crack will continue like that until it reaches the free point. Because there is no support here, so it will end here. So this part, this is the crack shape. So it's similar, quite similar to the slabs, the cracking lines for slabs, depend on how much is the support. So for example, if you have four supports like that, so we will have 45 degree, 45 degree, and here 45 degree, 45 degree. So this will be our cracking or two-way bending behavior of the wall. If you have four restraint, so restraint, 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 restraint. Okay, this are also reminder for last week lecture. And briefly, the design steps for two-way bending are: the wall is designed as a rectangular panel with lateral support at least along its base and one of its vertical edge. So again, this is what's meant. So we need to design for or the wall to be acting in two-way bending behavior. It should at least have its bottom side restrained and one of the vertical side restrained. So restrain here, no restrain here, no restrain here. This is the minimum. The wall is of a single leaf or solid construction or of cavity wall construction, with each leaf of the cavity wall being a single leaf or a solid construction. So we might have a single leaf wall. This is the cross section. Or it might have, so we have a space here and we have two leaves, for example. So this is single leaf and this is cavity wall. Okay. The requirements for robustness are satisfied for this type of masonry wall. The construction and the detailing of the wall are such that the requirement for clause 7.4 and 7.43 are satisfied. So all these are some conditions for the design of two-way bending. If the wall has an opening, the panel on each side of the opening is checked independently. So if we have a wall and we have opening here, so this wall will be subdivided to two walls. So this wall will be checked alone and this wall will be checked alone. So this in case of opening due to windows or doors and so on. So this all was a reminder or a revision of some of what we have last week. And now we can start introduction to reinforced masonry. The general requirements for reinforced masonry are the reinforced masonry are designed for four types of straining action. Design of member in compression, number one. Design of reinforced masonry member in bending, number two. Design of members for in-plane shear, number three. Design of member for out-of-plane shear, number four. So the reinforced masonry wall need to be designed for four straining action, compression, bending, in-plane shear, and out-of-plane shear. The design principles are similar to unreinforced masonry, but just the formulation of the capacity of the reinforced masonry increased due to addition of reinforcement. So the main idea is unreinforced masonry, same concept as unreinforced masonry, but the capacity are increased due to reinforcement or addition of reinforcement. This is logical because we are adding the reinforcement to enhance the probabilities or enhance the behavior of the unreinforced masonry. So let's see what is the reinforced masonry or how can we reinforce the masonry wall to be a reinforced masonry wall. This could be obtained by reinforce the masonry wall with cores of blocks within the core of blocks. So we have vertical bars. This is our first step. And then around the bars, we fill it with grout. So this is how we reinforce the masonry walls. So we add some bars and we have spacing between these bars. Okay. Then the vertical bars will be surrounded with grout to be fixed in place. So now this wall become reinforced with vertical reinforcement first, and as you can see here in this figure here, so we will add, like for example, bar here, bar here, bar here, then fill around the bar with some grout, some grout, some grout. The spacing between bars are the bar spacing. We have bar spacing. Okay, so this is the first reinforcement, vertical reinforcement. We will have also in bed or in the mortar bed or the mortar course reinforcement. or in other words, we can have horizontal reinforcement. So how we can reinforce the masonry wall? Using two types of reinforcement. One is vertical reinforcement, and second is horizontal reinforcement. So the horizontal reinforcement, as you can see, is traveling horizontally like that. So this bar, and we have also another one like that. These bars will be embedded in the mortar bed. Okay, like that. And this connection here is to make it more hard to be like taken off the wall. So this will make it more stable inside the mortar. So these are the two types of reinforcement we have in the reinforced masonry walls. So there is some general reinforcement requirements for masonry selection. The first one is the main reinforcement primary load direction. Axial compression, bending, shear, and tension must comply to or with clauses 8.5 to 8.10. So any reinforcement or the main reinforcement of the reinforced masonry wall should be complied with clause 8.5, 8.6, 8.7 up to 8.10 for all the design uh, actions, which is axial compression, bending, shear, or tension. So you need to check this reinforcement against all these clauses. The secondary reinforcement resist shrinkage, temperature localized, or loading must comply with clause 8.43 and not less than 0.00035 AD. So the secondary reinforcement need to be checked against clause 8.4.3, and the secondary reinforcement should be more than or equal to 0.00035 times a design of the reinforced masonry member. And the use of the secondary reinforcement to resist shrinkage, temperature localized issue, or temperature loading. So these are the use or the benefits of using the secondary reinforcement. If these two conditions, A and B, are not satisfied, so design the wall as an reinforced masonry wall. Or in other words, means neglect the reinforcement inside. Okay, so if these two conditions, A and B, are not there or are not satisfied, so this means that the added reinforcement are ignored or can be ignored. So this is an example on reinforcement. In this example, this is just we have this example within or along the lecture. So there's only very simple requirement here. Now this is an example, plan of a wall. The wall length is 2.6 meter or 2600 millimeter. The thickness of the wall can be 90 or 140 or 190. And as you can see here, we have some vertical reinforcement, each 800 millimeter. So spacing of the reinforcement is 800 millimeter. Okay, and as you can see, we have a bar embedded in grout within the voids of the masonry elements. So the vertical reinforcement, in the first and the mid and last cores, so each one of this is a core, are grouted and reinforced with N12 grade D500N. So this means how much is the total vertical reinforcement? So area SCT or area vertical, let's call it area vertical, equal to 4N12. This is based on what we have here. We have 4 bars. Each one is N12. The grade is D500N. For the horizontal reinforcement, we have N12, 20, grade D also 500N, located at the mid height and top of the wall. So if this is our wall, so this is height, and this is our mid height. So we have N 20 bar like that here, and at the top N 20 bar here. So how much is area horizontal? Area horizontal or the horizontal reinforcement is N2 N20. So we have two types of reinforcement. The first one is vertical, 4N12, and the horizontal reinforcement is 2N12, both of them with the same grade, D500N. So the requirement is very simple, just to know how to calculate how much is area ST or area S vertical and area S horizontal. So vertical reinforcement, as we know now, 4N12. So 1, 2, 3, 4 bars. Each one of them is N12. The spacing of them is 800 millimeter. Okay, so the area is the total area or the area of the vertical reinforcement will be area of 4 bars. So it is 4 by R squared. Each bar, this bar is a circle. So it has a diameter and also has a radius R. So area of a circle equal to by R square if you are using the radius, right? Or area of a circle is by D squared over 4 if you are using the diameter. Okay, so for N12, R is 6 millimeter, the radius is 6 millimeter. So by 4 by 6 square give us area is 452.4. For horizontal reinforcement, similar, we have 2 bars in 20. So if this our wall, again, we have 1 bar at the mid height here in 20 and 1 bar at the mid height here in 20. So total is 2 in 20. So area horizontal is again 2 by R square. The diameter here is N20, so the radius is half, which is 10 millimeter. So the total area of the horizontal reinforcement is 628.3. Okay, so this is an example of how to interpret the reinforcement of the wall given for a wall, and we will continue explaining some parameters of this example later during the lecture. Then, how much is the reduction factor for reinforced masonry? As you can see, for unreinforced masonry, we have different value for compression, for friction, for shear, and other action. So for unreinforced masonry, it is between 0.5 to 0.75. As you can see here, so we have this value, different value for the horizontal, sorry, for the unreinforced masonry. Okay, for reinforced masonry, we have one value, which is 0.75. So for reinforced masonry, phi is equal to 0.75. So this is the capacity reduction factor for reinforced masonry. Then our first formula or our first design action is design of reinforced member, reinforced masonry member in compression according to, okay, no worries, Harrison. So design the member of reinforced masonry in compression according to clause 8.5. So the formula is, or clause 8.5 has a formula of FD, the design force, should be less than or equal to phi KES times, in brackets, FM dash AB plus KC times FCG dash over 1.3 all to the power 0.55 plus 0.005 FCG dash times A gross plus phi R alpha R Fs yield AS. So actually we have three components for this formula. We have the masonry component, Fm dash AB. This is our first component. Our second component is the grout component. The ground component, which is this component here. So we have Kc times Fcg dash and so on. Okay. The third component, which is for the reinforcement component, which is alpha R Fs yield As. So this is our third component. And Kas is the cylinder reduction factor for the wall. Okay. So these are the parameters of the design of reinforced masonry walls in compression. Actually, we have a contribution of three elements in the compression. The first contribution is from the masonry component itself and from the reinforcement embedded inside and due to the grout surrounding the vertical bars. Okay, so these are the cylinder reduction factors. Sorry, these are the equation for the masonry, reinforced masonry in compression. And let's have a look in the standard about that. Let's have a quick look. So here, as you can see, this is the design of member in compression here. Close 8.1 and in 8.5, sorry. So 8.51 is the basic compressive capacity. So the basic compressive capacity, according to clause 8.51, as follows. So this is the formula. The design parameters of this formula are, as you can see, FD is the design compressive force acting on the cross section. Phi is the capacity reduction factor. KS is a reduction factor to account for the eccentricity in loading and slenderness of the member in design of reinforced masonry. And KS is given using this formula here. SR is the slender ratio. E is the effective eccentricity. FM dash is the characteristic compressive strength of the masonry. AB is the bedded area of the masonry cross section. KC is a strength factor for grout in compression. 1.4 or 1.2 based on masonry type. FCG dash, the design characteristic compressive strength of the grout in MBA. A gross or area grout, sorry. AG area grout, design cross section of area of the grout in reinforced masonry member. FS yield is the design yield strength of reinforcement. AS is the total cross section area of the main reinforcement. Alpha R is the reinforcing contribution factor. 1 for beers, 0.4 for walls, 0 for concentrated loads. So these are a brief introduction of the formula we are using for compression design here, and the parameter are defined clearly in the standard. So calculation of the slenderness ratio SR is identical to that required for the refined calculation procedure in 7.3.4.3. So SR will be according to clause 7.3.4.3. The reduction factor KES is equal to 1 minus 0.025 times SR multiplied by 1 minus 2 times E over T. So this is our reduction factor KES. For conservative design, the eccentricity shall be taken as 0.05 thickness of the wall. The reinforcement area AS should be more than or equal to 0.002 area design of the wall. So it's just this is just a few example of the parameter needed. So for the detailed calculation, we need to refer back to section 0.8, sorry, section 8.5 in the Australian standard 300 or sorry 3700. Okay, so this is the main parameters we have. And this is how to find the slenderness ratio SR according to clause 7.3.4.3 for a wall that is laterally supported along one or both of its vertical edges and subject to design compressive force FD less than 0.2 F0. SR will be the lesser of these two values. Okay, so if we have a wall that support on one or two vertical sides and the bottom side, so the top side may be restrained or not restrained, SR will be using the lesser of these two formula. So SR equal to AV times H over KT times T. H is the wall height and T is the wall thickness. Or 0.7 over T AV H AHL. So H and L, wall height, wall length, wall T and wall thickness. So what is AV and AH? If we go to the standard again to find the clause 7.3.4.3, here design using refined calculation. So here is the refined calculation. So if we go scroll down until reaching the slenderness ratio. So here, as you can see, is our slenderness ratio. So the slenderness ratio of a member about a given principal axis shall be as follows. For a wall that laterally supported along one or both of its vertical edges and subjected to design compressive force, so FD SR will be the lesser of these two. Okay, where SR is the slenderness of the member, AV is a vertical cylinder coefficient equal to 0.75 for wall laterally supported and partially rotationally restrained at both top and bottom. So if you have a wall restrained at top and bottom end, so AV shall be taken as 0.75. For wall laterally supported at top, bottom, and partially restrained at one of them, so 0.85. One for wall laterally supported at both and bottom. So depend on if it is partially or totally supported laterally. So here can be AV can be 0.75 or 0.85 or 1 or 1.5 or 2.5. So for freestanding wall, it's 2.5. H is the wall height, clear height of the wall between horizontal lateral supports. KT is a thickness coefficient derived from table 7.2. T is the overall thickness of the wall cross section perpendicular to the principal axis. AH similar to AV. AH is horizontal slenderness coefficient. It depends on the vertical edges sub restraint. So it can be, so this one will depend on here. So it can be 1 or 2.5. So 1 for wall laterally supported along both edge regardless of the rotational restraint along this edge, or 2.5 for wall laterally supported along one or vertical edge. So for this one, AH equal to 1. The other option is only one end, so AH will be 2.5. L is the clear length of the wall between the vertical supports. So those are the parameters of the slenderness ratio calculation according to 7.3.4.3. The second case, if we have opening, where opening in a wall are such that the masonry between any two consecutive openings is by definition an isolated pier. The slenderness ratio of that isolated pier shall be taken as SR equal to 2 times H1 over T, where H1 is the taller opening height. For all other cases, SR is equal to AV times H over KT times T. Okay, so if we return back to the standard, so B, where opening in a wall such that the masonry between any two consecutive opening is by a definition of an isolated pier. The slenderness ratio of that isolated pier should be taken as the lesser of the following. Number one, SR 2H1 over T, or the value of the pier assessed in accordance with this clause. So we will focus on this one, similar to the slide, where SR is the slenderness ratio, H1 is the height of the taller opening, T is the overall thickness or depth of the member perpendicular to the principal axis under consideration. So where opening in a wall are such that the masonry between any two consecutive openings is by definition an isolated pier. So if we have a wall with two openings, so we have this is our pier. So this now becomes called pier. So the slenderness ratio of that isolated pier, the green isolated pier, will be 2H1 over T. Okay, 2 is okay. H1 is the height of the taller opening. So if we assume this is, for example, 2 meter, this 2.5 meter. So this is our H1. So H1 is 2.5 meter. T is the overall thickness of the wall. So this is our T. Okay, so this just briefly explanation of what is meant here for the slenderness ratio. All other cases, so this is the formula. Then second design action we have today is design of masonry. Reinforced masonry members in bending. The bending is according to clause 8 or section point 6, 8.6. So the portion of cross-section area of the main tensile reinforcement used for design purposes, ASCD, must be the lesser of the cross-sectional area of the fully anchored main tensile reinforcement, AST, or the quantity given by this value. So to design the member in bending, we have a value is of the area is called or named ASCD, which is portion of reinforcement used for design of bending. So this just means that you may take the whole amount of steel embedded in the wall or part of it. So ASD will be the lesser of two values. These two values are the total area of steel or the value 0.29 times 1.3 Fm dash B D over F is yield. So this is the formula. So let's define some of the parameter. So area ST is already the area of steel, and here we have Fm dash, we know it earlier, minimum compressive strength, B and D, the properties of the wall. So Fm dash again is the compressive strength of masonry. B is the wall member width. D is the effective depth of the steel reinforcement. So what we don't know is if a yield is grade of steel. So the grade of steel will be found using table or the design yield strength of steel or grade of steel. Will be from or using table 3.7 strength and ductility of reinforcement. So we may have these types of reinforcement. So we have bar plane, bar deformed, welded mesh, stainless steel plane, stainless steel ribbed bar. So for example, the example was given to us earlier. It was D500N. So how much is the design yield strength? 500. So for D500N deformed bar, if its yield equal to 500 MPa. Okay, so this for the steel grade, and this is another step of the example we had earlier. We need to find how much ASD used for design if knowing the vertical reinforcement in the first, mid, and last cores, grouted and reinforced with N12 grade D500N. Fm is 7.2 MPa. So again, we have for N12, the width of the beam of the wall B is 200, 2600. The width of the wall is 400. So this is all what we know. So let's find how much is ASD. As you know, ASD again is the lesser of AST and 0.9, 0.29 times 1.3 Fm dash times B times T divided by Fs yield. So, as you know, we find AST earlier, it was 452 for 4N well. D, the effective depth of the reinforced masonry member is for 140 over 2 equal to 70 millimeter. How can we find that? So this is our wall. This is our reinforcement. So if this our moment, out of plane moment, so D is the distance from the top fibers to the centroid or the CG of steel bar. So this is our D. So D equal to T over 2, because this is total is T. T was given as 140 millimeter over 2, so this is 70 millimeter is the effective depth of the reinforced masonry member. So if we substitute, so this one is 452.4 millimeter square. This is 0.29103. Fm dash was given as 7.2. B, width of the wall 2600. D of the wall is 70. Fs yield is 500 because this is D in D 500 N. So this is 500. So this give us a value of 988.3 millimeter square. So our value should be this one here. So this should be our value. So ASCD is 452.4 millimeter square. This is our answer or our required answer for this question. So this just simple step how to know how much is ASD. So let's refer back to the standard to see clause 8.6 or section 8.6. Design of members in bending, as you can see. So this is the formula, 8.6. So the formula we will be using for bending of reinforced masonry member, MD should be more than phi Fs yield ASD D times 1 minus 0.6 Fs yield ASD over 1.3 Fm dash BT, where MD, the design bending moment, phi reduction capacity factor, Fs yield, the design yield strength of the reinforcement, ASD is the portion of the cross section. So this one, what we have calculated earlier, the lesser of ASD and this value, where D is the effective depth, Fm dash characteristic compressive strength, B the width of the masonry member, AST is the cross-section area of fully anchored longitudinal reinforcement in the tension zone of the cross-section. So this is the formula we will be using to design for bending. So design of members in bending. The main reinforcement in the direction of bending must be spaced at this some instructions or conditions need to be satisfied for the reinforcement. Be spaced at center not exceeding 2000 millimeter. So the spacing between the bars cannot be more than 2000 millimeter. Bar. Include an area of at least 100 millimeter within 300 millimeter of the edges of the member. And number 3 is MD shall be more than 1.2 bending capacity of the unreinforced masonry. So we have 3 conditions for the reinforcement. We need to have spacing less than 2000. For the wall, you need to have at the first 300 millimeter of the wall, both edges, this green area, you need to have a reinforcement area of 100 millimeter. squared. The third is MD for reinforced masonry should be more than or equal to 1.2 or MD for URM or unreinforced masonry. For members subjected to two-way bending, the requirement for the main tensile reinforcement must be satisfied in each direction. So if you have two-way bending, like something like that, so you have two direction of bending, so you need to satisfy the condition in both directions. So here, the design formula we have seen in the standard, clause 8.6. So the design formula, MD should be less than or equal to phi, FS yield, ASD, sorry, D times 1 minus 0.6 AFS yield, ASD divided by 1.3 FM dash BD. Phi is the reduction factor according to clause 4.4. FS yield is the design strength of steel. So for example, again, D500N, FS yield is 500 MPa. ASD is the portion of the cross-sectional area of the main tensile reinforcement used for design, which is the lesser of these two values. D is the effective depth of the reinforced masonry member, FM dash, characteristic strength, B, width of the masonry member, AST, cross-section area of the fully anchored longitudinal reinforcement. So this is the formula. We have go through it earlier in the standard. Okay, number 3, design of reinforced masonry member in plane shear. So the third design action we have is in plane shear, which is according to clause 8.7. So clause 8.7, as mentioned, the design requirements are similar to what you learned in unreinforced masonry wall. So we will follow same procedure in unreinforced masonry, but due to the addition of steel reinforcement, the capacity of masonry wall will change or mainly increase. So the capacity increase due to addition of the reinforcement. To find in-plane shear capacity, the walls are divided to two categories, category number 1 and category number 2. Category number 1 is long walls, which is height over length is less than 8.3 according to clause 8.7.2, or short walls, height over length is more than 2.3. So these are long wall. And these are short wall. So if this wall, so this is our short wall. So this is L and this is H. So here for short wall, the height is bigger, high over length, be more than 2.3 because the height is much bigger than the length of the wall or the width of the wall. Here for long walls, we have this is L and this is H. So this is long wall. So L here, H over L here is small because H is smaller here. So H over L is less than or equal to 2.3. So this is the classification of walls for in-plane shear, long and short walls. So each type of them will have different procedure. Let's have a look on 8.7 in the standard. So for 8.7, this is the close. So we have 8.7. We have long walls and we have short walls. So for long walls, the condition is H over L less than or equal to 2.3. The design shear capacity is VD less than or equal to phi FVR AD plus 0.8 FS yield AS. For short reinforced wall, the condition is H over L more than 2.3. Subject to in-plane shear shall be designed according to clause 8.8. If we go to 8.8, we will find that 8.8 is out of plane shear. So let's go back to our slides. So here for long walls, clause 8.7.2. Long walls, when the wall is less than 2.3, H over L less than 2.3. So this in plane shear. So we have the formula. Is this our formula? We have FD, the design shear force, should be less than or equal to phi reduction factor times two component. The first component FVR-AD, which is for the masonry component, and the second component is zero point 0.8 FS yield times AS for the reinforcement component. So for in-plane shear, there is no rule for the grout. So we have only masonry component and reinforcement component. This because the grout is very weak in plane shear. Where FVR is the effective shear strength, which is equal to 1.5 minus 0.5 H over L. AS is the cross-sectional area of reinforcement. We have two conditions for it. So we have if H over L more than 1, AS equal to area is horizontal over times L over H. And second is if H over L less than 1, AS equal to the total cross-section horizontal reinforcement or the total cross-section area for vertical reinforcement, whichever is less. Okay, so what this means? Just a second. So if we add slide here, so for this one we have again VD should be less than or equal to 5 times FVR AD plus 0.8 FS yield AS. This is the contribution of masonry. and this is the steel or reinforcement component. And this is our design in plane shear force. So FVR equal to 1.5 minus 0.5 H over L. So FVR is effective shear strength, where H and L, H is the wall height, L is the length. This wall is long wall, so H over L less than or equal to 2.3. Okay, so this for FVR. For AD, AD was defined earlier as I'm just trying to find it. So AD is the design cross-sectional area. For the masonry unit according to clause 4.5.6. So we have this is FVR, AD. Now AS is the parameter we need now. AS has two cases, or can have two cases. AS is equal to the horizontal reinforcement times L over H. This condition when H over L more than 1. So if H over L more than 1, so this is our area S. Area S is the design or the cross-section area of steel. Used to resist in-plane load. And the other option is AS will be the total ASH or total AST, whichever is less. So we will take the smaller of this one or this one. So the smaller of ASH or AST. So this case number A, this case number B, and this case only when H over L less than or equal to 1. So if H over L more than 1, take AS equal to this value. If H over L less than 1, take the lesser of ASH and AST. Okay, so this is our formula for the in-plane shear for long walls. in plane shear for long walls. Then there is a short example for reinforced masonry. Same example. Reinforced masonry wall has length of 2.6, height of 3. So L is 2.6 in this case. H is 3. What is AS? The cross-sectional area of reinforcement. If vertical reinforcement is 4 in 12, grade 500. Horizontal reinforcement 2 in 20, also D 500N. So it is a continuation on the example we started earlier, but in this step we are finding how much is AS. So from our previous calculation, we knew that ASH equal to 2 in 20 equal to 628.3 millimeter squared. From the given parameters, we have H over L equal to 3 over 2.6, which give us a value of 1.15, which is more than 1. So the wall classification is long or short. It is more than 1 and less than 3 point or 2.3. 2.3. So if it is less than 2.3, it is long wall. Okay. For AS has two cases as we mentioned. If H over L more than 1, if H over L less than 1. So we are in the first case. So AS equal to AS horizontal times L over H. So AL horizontal is 628.3 millimeter square. L is 2.6, H is 3. So this gives us a value of AS equal to 544.4, sorry, 0.54 millimeter squared. So 544.54 millimeter squared. This is our AS. The other option, if H over L less than 1, so we will use AS equal to ASH or AST, whichever is less. So actually in this problem, we have calculated both together, both earlier. So area SH was 628.3. Area ST was, I think, 400 something or 500 something. 452.4. So if, for example, we have the second case, so this will be our value. Okay, it's just a brief practice, a short practice on the steps. Now, the second case we have is if we have reinforced masonry member in plane shear but short wall. So if you have H over L more than 2.3, the standard asks us to design this type of walls using clause 8.8 or as out of plane shear. So if you have a short wall, this H and this L, and you find h over L more than 2.3. So this is a short wall. So a short wall is designed as out of plane shear wall. Okay. So if you return back to the standard, the clause we had just read earlier. So for short walls, when h over L more than 2.3 shall be designed according with clause 8.8. 8.8 is design of walls for out of plane shear. So it will be designed as it is out of plane shear. Okay, so now the fourth straining action or design action we have is design of reinforced masonry member in out of plane shear or according to clause 8.8. So we have two cases here or two examples for in plane shear wall, short walls, similar to that. This is a short wall, h over L less than 2.3, or for out of plane shear, which means loads are perpendicular to the wall for long walls where h over L more than 2.3. So this clause 8.8 is used in these two conditions or two cases. The formula for out of plane shear is VD should be less than or equal to phi. We have three components participating in the out of plane shear capacity. The first one is FVM dash BWD. This is the masonry component. And we have V FVS times AST tension steel component. And we have FS yield times ASV times D over S shear steel component. So in this case, we have three contribution, number one, number two, number three, from masonry, tensile tension steel, and shear steel. Okay, but there is a condition in the standard that VD should be also less than or equal to 4 pi V FVM dash BWD. Okay, so this is the conditions we have where BW is the width of the web, D is the effective depth of the reinforced masonry. So if we have, this is our wall for out of plane. So the longitudinal, sorry, the vertical bars will be our tensile reinforcement. Okay. And BW will be the width of the wall. D is the effective depth of the reinforcement. So in a different color, this might be D. Depend on the moment direction. But anyway, this is D. from the top to the bar. So the effective depth of the reinforced masonry wall. FVM dash is between point is sorry 0.35 MPa. FVS 17.5 MPa. S is the spacing between the shear reinforcement. The shear reinforcement is the horizontal reinforcement if there is any. So this is our shear reinforcement. So S will be the distance or the spacing between the shear reinforcement. So VM dash is equal to 0.35 MPa, and it is the characteristic shear strength of masonry. That's why it is too small. FVS is the design shear stress of steel. And FS yield is 500 MPa, for example, if we have D 500 N, the grade of steel. So if we look at our example, the example we have go through earlier. So the vertical reinforcement is 4 in 12. This is our vertical reinforcement. And the spacing of this reinforcement is given as 800 millimeter. So this is AST. The horizontal reinforcement or the shear reinforcement is our horizontal reinforcement. We have 2 in 20. This was given. BW is the full width of the wall, or 2600 millimeter. This is BW. D, this is a note here. D, for out of plane shear calculation of partially grouted wall, the value of D should be conservatively considered equal to the face shell thickness. So in this case only, because the whole wall not grouted, so as you can see here, there is no grouts here, no grout. This make the wall weak at this point. Okay, so that's why there is a condition here to use D as the face shell depth. So in this case, we will be using, this is our D. Okay, so just because the wall is not fully grouted, it is only grouted when we have the bars. That's why conservatively we reduce D to only the face shell. For ACT, it has also a condition here for out of plane shear. ACT in shear is a bit different to the compression. So in compression, it has a different value. It was the minimum of 2 values. If you remember, it was just a second, guys. So AST in comparison, it was should be more than in comparison AS it was should be more than 0.002 AD. This was the condition for comparison. But here ACT will be the lesser of vertical reinforcement area and 0.02 BWD. So AST in this case would be equal to the lesser of AST and 0.02 BWD, where BW is the wall width, D is the effective depth of the wall. Okay, so I think that's it for today lecture. Do you have any question, guys? That's it for the reinforced masonry walls. And if you have any questions, just let me know. Thank you, Harrison. Thank you. See you in the class. Thank you. Okay, bye.